So we're going to have an introduction to rotational dynamics. Rotational dynamics are going to describe the relationship between forces that cause rotation and then the motion that results from those forces. So we're going to be talking about torque, rotational kinetic energy, work that's done by rotational motion, and momentum. We have angular momentum and the idea of a moment of inertia. So let's start with a moment of inertia. Moment of inertia of an object is the same thing as mass in linear dynamics and kinematics. It is the thing that resists the change in motion, either starting up, slowing down, changing direction, resists any of those changes. You think about the moment of inertia, you want to think about the idea that you're taking all of these individual little chunks of mass and how far away they are from the center of rotation and adding all that up and compressing it into a singular thing, which is the moment of inertia. And so the moment of inertia is going to depend on the mass and the radius. It's going to depend on the geometric shape. Is your shape a solid disk? Is it a hollow tube? They all react differently rotationally. So hoops are going to roll different than disks. Hollow balls roll differently than solid spheres. So we'll do an example of that to kind of show you how that works. So here's our example. I picked a solid sphere and a hollow sphere, and you'll notice that each different shape has its own equation that represents the moment of inertia because you have to take into account the geometry. You won't have to memorize these. They'll be given to you if you need them, so please don't panic. So we'll start off. We have two spheres that are matching in geometry, but and mass, but the distribution of those things is slightly different. So for a solid sphere, you have a moment of inertia that is 2 times the mass times the radius squared, all divided by 5. When you plug in the numbers that I picked, the 20 kilograms and the half meter mass, you end up with 2 kilogram meters squared. Then you do the same math for the hollow sphere, which has an equation of 2 times the mass times the radius squared over 3, you end up with something slightly larger, which tells you that if they have the same mass, that hollow sphere is going to resist motion more than the solid sphere. So it's going to be harder to get moving, it's going to be harder to stop, and it's going to be harder to have it change its direction. Another quantity for rotation is work, and another one is kinetic energy. We're talking about motion, so of course kinetic energy is going to be part of this. Wherever you have kinetic energy, you're going to end up doing work. And so this is going to happen when you're starting up a motor or making an object starting to roll. If you make an object roll, it takes work. And you're going to look at the perpendicular force to the motion, just like you do with torque, and notice that torque is part of this. It should make sense. If linearly work is force times distance, in the rotational physics world, work is torque times the angle. And you also get that work is the change in rotational kinetic energy. So rotational kinetic energy is 1/2 I omega squared, where the moment of inertia has replaced mass and omega has taken the place of velocity. We have conservation of energy in rotational physics. It's going to be potential energy plus translational, which is the linear kinetic energy, the usual 1/2 mv squared. And then we have this rotational kinetic energy because it's moving, but it's spinning or rolling. And you have to add all those up to get the total energy. So if you think about rolling down a hill, we talk about the conservation of energies with rolling down a hill. You start off at the top of the hill, you have the gravitational potential energy is all the energy at the very, very top. It's sitting still, and then it starts to roll. And it's anywhere along that hill as it rolls down, you're going to have the gravitational potential energy plus the translational potential energy, the 1/2 mv squared piece, plus the rotational kinetic energy, which is 1/2 m omega squared. Momentum is another quantity that has an angular piece to it, and it's that delta L. It's going to be the moment of inertia times the angular velocity, or torque times time. Hopefully that looks familiar. Remember, in the linear world, momentum is mv, or it is force times time. Hopefully it all looks familiar. Here's an example with the rolling down a hill idea. So is it faster to slide down a hill or roll down a hill? So we'll take the idea of a solid cylinder, because we are going to end up using the moment of inertia, so we have to pay attention to the geometry. And we're going to put it at the top of a 3-meter hill. First, we're going to deal with sliding. So all of the energy is going to be that translational kinetic energy. So all of your potential goes to translational kinetic energy. We're assuming there isn't any friction. You run through the math, and you get a speed of 7.7 meters per second. If you take that it's going down the hill while rolling, then you get the potential energy at the top, plus the translational kinetic, plus the rotational kinetic energy. You plug in the appropriate pieces, you get to cancel some things out. That's always nice. Clean up your equation a little bit. And if you work through the math, you end up with the velocity of 6.2 meters per second, a little bit slower. So it's actually faster to slide down a hill than roll down a hill. And notice in the canceling on both of them, the masses went away. So the mass didn't matter in either one, which is how Galileo came up with the idea of everything falling at the same rate. He did this experiment, basically rolled cylinders to see that no matter what size the cylinder was, it came down the incline at the same rate. Alrighty, bye-bye.